for the introduction. Yeah, it's a pleasure to take part, remotely at least in this conference, thanks to modern technologies. I would really like to be there, but yeah, traveling now is challenging, as those who arrived in person, I think I can appreciate, yeah. And I really appreciate also the courage of Federico, Iggy, and other organizers to set up this meeting, during all these uncertain times. Okay, so by the way, feel free to interrupt me, like with questions during my talk. I will be glad to answer. Okay, you see my title, and yeah, this is work I have been doing recently with Andrei Shkerin. Let's move. So it will be about primordial black holes, and here there is a summary of constraints on primordial black holes with masses from about 10 to minus 15 to 10 to 20 solar mass. Okay, I just took this this plot from this paper, and yeah, that's like recent review. And yeah, you see here there are many constraints. So that's really multi-messenger astronomy. So there are constraints from lensing, there are constraints from dynamical like effects of primordial black holes. And yeah, what is constraint is the abundance of black holes in units of the fraction of total dark matter mass. Okay, so in this range, they are well constrained below 1, so they cannot be the full dark matter. Interesting, there is some window here, but that's not what I'm going to talk about. I'm going to talk rather about this range, actually the one even to the left. So here you see there are strong constraints. Actually, where do they come from? They come from the idea, from black hole evaporation. So the black holes lighter than 10 to minus 17 solar masses, or 10 to 17 grams. Yeah, funny, there is this coincidence in numbers or in powers. They decay before now. They decay by now, and yes, in this range they would produce a lot of hard radiation that we would detect, say in gamma rays or X-rays. And yeah, let me start with a kind of crash course on Hawking radiation. So the temperature of black hole is inversely proportional to its radius, which is itself proportional to the mass. So the temperature is inversely proportional to the mass. The lighter is black hole, the hotter it is. And due to this emission process, the mass of the black hole changes. Yes, so the mass of black hole decreases. Well, according just to the like the radiation is proportional to the area and proportional to the force power of the temperature. So we get that the black hole lives a finite amount of time, which strongly depends on its mass, on its initial mass. And we see from here that like black holes with like stellar black holes, they are safe. They will never evaporate during lifetime of universe, or even many lifetimes of the universe. On the other hand, light black holes will evaporate, and actually the lighter they are, the faster they do that. Yeah, another thing to say that black holes, they believe to emit all particles. Yeah, so they just have this temperature, and they will produce all particles that are accessible energetically. Yes, so whose masses are less than the temperature of the black hole. And that will also accelerate evaporation, at the later stages where black hole can emit more species of particles than in the beginning. Well, anyway, so like from these estimates, or maybe more precise calculations, we can conclude that black holes with masses from 10 to 9 to 10 to 17 grams, if they are produced in the early universe by some mechanism, they would evaporate between Big Bang nucleosynthesis and nowadays, and hence the kind of the remnants of their evaporation, they would affect dynamics of the universe, which we can probe. And there are constraints, but actually pretty strong constraints on abundance of black holes with these masses, due to effective number of degrees of freedom, like BBN dynamics, spectral distortions also, spectral distortions about which we heard in the previous talk, and so on and so forth. On the other hand, you can also say that they can be very actually interesting for this type of observables. On the other hand, the black holes with initial masses below 10 to 9 grams, so really tiny ones, they would evaporate before BBM. And hence, it looks like there are no constraints on them. Well, recently there has been some renewed interest in this type of black holes because they can do, like people consider various scenarios with their participation. For example, this black hole, they can reheat the universe after inflation. They can produce heavy dark matter, yeah, because black holes produce everything, including dark matter. And actually, they produce all particles up to Planckian masses. Yeah, so they can produce some heavy dark matter, which like heavy remnants, which maybe may play the role of dark matter now. And or they can even participate in leptogenesis and so on and so forth. So the question is that I will address and will study, are there really no constraints actually on this type of black holes? And it has been suggested that actually there are very strong constraints on these black holes, kind of ultimate constraints you can imagine. And that was suggested in these works by Ruth Gregory, Jan Moss, and collaborators, where they started from the following observation. We know that according to the currently measured values of the parameters of the standard model, in particular the Higgs coupling and the top-Yukawa coupling, for these parameters, the potential of the standard model Higgs is, well, turns around. Yes, so normally we would say it's lambda phi to the 4 that grows up, but then due to radiative correction, it turns around and the quartic coupling goes negative and the whole potential goes negative. And the values of the Higgs field around 10 to 10, 10 to 11 GeV. And that means that our electric vacuum where we live now is actually metastable. So it can decay to this domain of lower potential energy. The decay rate is exponentially suppressed because it's a tunneling process. So naturally, it's natural that it's exponentially suppressed. And in flat space or in empty space, like in current universe, if you want, it is very strongly suppressed. So the suppression factor B0 is something like a few hundreds, actually even a few thousands, I think. Yeah, a few thousands. So it's inversely proportional to the Higgs coupling constant in this range, in this region, which is tiny, which is small. So the lifetime of our electric vacuum is somewhere around 10 to 400 years, maybe 10 to 1,000 years, but that doesn't matter much because it's obviously well above any reasonable any reasonable values, well beyond our horizon. But as for any tunneling process, the suppression decreases when we increase temperature, and hence the rate grows, and actually grows exponentially. So at some, at high energies, it's expected to be given by this Boltzmann kind of exponent, where now instead of this B0, we would just have the ratio of the Sphaleron energy to the temperature. And Sphaleron energy, or Sphaleron, it's also called critical bubble. Yes, so it basically gives us the value of the potential energy between the two vectors. Yeah, the false one and the true one. And it's somewhere around 10 to 12 GeV if you estimate it for the Higgs potential. So if at some stages in the universe, the universe would have temperatures above 10 to 12 GeV, the Higgs vacuum may be destabilized. In fact, the story is a bit more complicated. And in standard model, apparently this would not happen if you just change if you just heat up the primordial plasma. Then also the Higgs potential itself gets thermal corrections, which give large thermal corrections to this Sphaleron energy. And eventually, depending on the coupling, the precise value of the couplings, they may or may not stabilize the Higgs vacuum, the electric vacuum completely, or maybe not completely. But anyway, at high temperatures, the decay probability is exponentially higher. Are there any questions? I don't see any.
Yeah, go ahead.
Okay, good.
Questions from everyone? Oh, go ahead.
Sorry? Okay, I'm going ahead.
Go ahead.
Yeah. So now, yeah, let's now introduce black holes in this picture and basically combine the two observations that electric vacuum is metastable plus primordial black holes evaporate. So they evaporate, and then, as we discussed, as I discussed, there in the course of evaporation, the black hole temperature grows and perhaps goes up to Planckian scales. Well, we expect it to go up to Planckian scales. So it will scan all temperatures up to ultimate one, and then it explodes. So that suggests that the kind of due to this heating, the decay of false vacuum will be strongly catalyzed. And indeed, kind of calculations, some simple calculations tell that this suppression exponent B decreases when the black hole mass decreases. Yeah, and from the value of something like a few thousandths or a thousand, it actually goes down to order one at the black hole mass about 100 Planckian masses. So these black holes are still large in the sense that we believe they can be treated semiclassically as semiclassical objects, and the exponential suppression then is one, which means it's actually not there anymore. So this decay process is no more exponentially suppressed. And if you want, this is like an ultimate messenger for this type of black holes. Yeah, when before evaporating, they trigger the decay of our vacuum into some true vacuum with completely different properties. And I mean, that produces a bubble of the true vacuum, which expands with the speed of light and and reaches us. Okay, it's a spectacular signature, but we perhaps won't be able to analyze it. Turning the argument around, you can say this produces super strong constraints on this type of black hole. Basically, we should not have any black hole which would evaporate by now in our causal path. So there must be zero number of them. And that's a strong statement. So it's worth scrutinizing whether this conclusion has any caveats. And actually it does, because the calculation that I mentioned that tells that the suppression, exponential suppression disappears, uses like standard Euclidean approach to tunneling. When we consider, like, we find the tunneling solution is found in Euclidean time. Yeah, basically the dynamics is continued into Euclidean time, and one looks for bound solutions for black holes that has certain twists. But anyway, that's how this result was obtained. And that's actually not what we want, because this technique corresponds to thermal equilibrium. Yeah, this Euclidean picture. And in the context of black holes, it corresponds to so-called Hartle-Hawking vacuum, where black hole is actually assumed to be immersed into thermal bath with the same temperature. So it's not surprising then that indeed we get vanishing of suppression due to the thermal effects. But that's not a realistic picture. Realistic picture is a black hole immersed in a colder medium. Yeah, if we are talking about black holes with almost Planckian temperature. So we only have outgoing radiation, but we don't have any incoming one. And that decreases both like the density of the radiation, and also it actually eliminates particles like quanta, which could collide with this high energetic quanta and produce something non-trivial. In the context of black holes, this state with emission, where we only have emission but no absorption, is called under vacuum. And the question is how to calculate the probability of decay and how to do it for this realistic picture. It was suggested by several groups, including the group I list here, that in this realistic picture, perhaps the exponential suppression does not disappear completely. So the picture can be that with decrease of black hole mass, the exponential suppression, well, it's natural to expect that it somewhat goes down. Yes, so probability increases. Black holes do catalyze vacuum decay, but not 100%. Yes, so it's still some exponential suppression persists even for very light and hot black holes. And it can just go either to some minimal value, or maybe it even reaches certain minimum at some finite value of black hole mass and then goes up again. That's another option. And two arguments were given in this work. So one is the following. So consider a black hole which is very hot. Yeah. So hot means that it's also small. So it's much smaller than the size of the critical bubble that we want to produce, and that would trigger the false vacuum decay. Then this critical bubble, it's a semiclassical configuration. It must be made of soft quanta or with the size of order, with the wavelengths of order the size of this critical bubble. Indeed, due to thermal effects, the occupation number of the soft quanta near a black hole is enhanced, because it's just given by the ratio of black hole temperature to the frequency of this quanta, and this ratio is large. The frequency of the quanta we're interested in is much below the temperature of the black hole. Okay, so that's how this thermal argument works. But we don't want the occupation number of this soft quanta near black hole. We need the occupation number of this soft quanta at the scale of the bubble. So at the distance of the radius of the bubble, and at that distance, due to just dilution of flux in 4 dimensions, the occupation number will be suppressed by the ratio of black hole radius to the critical bubble radius squared. And then if we combine all these factors, we get actually that this density or the occupation number of soft quanta at this large distance is much smaller than 1. And we just don't have enough quanta to produce classical critical bubble. So yeah, exponential suppression must persist. Second argument is even stronger, because it says it also, now it says, let's recall also that use this formula for the density of the soft quanta, where I just put ratio of temperature to the frequency. But actually, that's actually not quite correct, because when black hole emits this soft quanta, black hole is not actually a perfect black body. It also has certain gray body factors, what is called gray body factors, due to geometry of this black hole. Actually, I will talk more about where this comes from. But due to these gray body factors, suppression of soft quanta is suppressed by the following product. So it's omega times the radius of black hole squared. So the probability to emit one soft quantum is given by this ratio, which is small. And we need, if we want to produce critical bubble, we need a semiclassically large number of them, like some number inversely proportional to the coupling constant. Hence, we need this probability of a single soft emission is multiplied. Exponentiated in the number of soft quanta we need. So we get some small ratio to the power 1 over alpha. So that's exponential suppression. And that's a very good argument, which I think convincingly shows that indeed this process must be exponentially suppressed. But this is just a heuristic estimate. Yeah. So we actually want to know how to calculate this B means and this minimal suppression here or here more precisely. Because even if this exponential suppression persists, the universe is big, and if we started populating it with primordial black holes, it's likely we'll have a lot of them, in the universe. So again, that will be an exponentially large number, just total number of these primordial black holes in our causal past. and we need to compare two exponential quantities. One is exponentially large number of black holes, and the other is exponentially small probability that they trigger vacuum decay. Yeah, and which one will win? We don't know. Any questions? Okay, I don't see any. So, yeah, I'm not following Slack really. Yeah, there is a lot. Yeah, anyway, I will look into Slack afterwards. Okay. Huh?
I will tell you there's something on Slack for a while.
Okay, yeah, okay, then I will answer those questions after. Okay, so yeah, I think I gave like phenomenological motivation why it's interesting to consider to study more in detail vacuum, well, black hole catalysis of vacuum decay. There are also other reasons. Let me quickly go over them, which are maybe more on theoretical nature, but I think they are worth mentioning. So first of all, this is just like a fascinating theoretical question. Yeah, how do we do that? How do we study these non-perturbative processes? And usually, when we do some progress in this direction, we learn something about quantum field theory. In this case, quantum field theory in curved space-time with non-trivial boundary conditions and so on and so forth. So we may expect to get some lessons about this. So second, that being a semiclassical process, it's in principle possible to include effects of gravity, you know, on this process, gravity itself. For example, how the metric of black hole changes in this process. And that likely will teach us something about maybe even quantum gravity in well, semiclassical quantum gravity. And like lessons could be similar to what we learned from Coleman-Deluche or Hawking-Moss instantons in de Sitter space, with all implications for inflation, stochastic inflation, and so on and so forth. And finally, maybe that's a bit like a long way to that, but nevertheless, that given that in this process, in principle, the mass of black hole can change and perhaps even decrease, like it was shown in these original papers by Gregory et al. So one can ask what happens with black hole entropy? Where does it go? And or how, say, the probability of this rare process, how it's related to entropy? Does entropy decrease, increase? I mean, yeah. So this type of questions, perhaps we can learn something about them considering this process. Okay, so now coming to like more concrete calculation. At first it seems okay, fine. We in principle know how to describe tunneling phenomena. Yeah, we have this Euclidean formalism, so maybe we just need a small modification of it. But yeah, when you start thinking a bit more closely, you realize that these technical questions, they may be more conceptual, because, for example, one of them is where should we look for this for the bound solution, semiclassical solution that would describe this tunneling? In which time does it live, for example? So in flat space, we know what Euclidean time means, but in curved geometry, there are different choices of time. And in particular, in black hole metric, there is Schwarzschild time, there is Kruskal time, which corresponds to the full extended black hole metric. But in this Kruskal time, the black hole metric is not static or stationary anymore. So which time should we continue to Euclidean space, to Euclidean like values? It's not clear. So second, it's not clear which Cauchy surface we should choose to define the state of quantum fields, yeah, the vacuum, because again, maybe or actually not maybe, but when we do physics in black hole background, or if you open a textbook on quantum field theory and black hole background, you will find that quantum fields are quantized on the Cauchy surface that goes to the whole extended black hole space-time, which covers, you know, the surface has part both in our universe, yeah, like outside of black hole, but it also has part inside black hole, like this black hole, I mean, this part of this diagram, and moreover, it even goes to another fictitious universe on the other side of the Einstein-Rosen bridge. And if I start like enforcing my boundary conditions or initial conditions on this surface, it looks like I will be sensitive to what happens inside black hole, like in this inner region or even in this fictitious universe, which does not seem to be right. Yeah, somehow what an observer sees outside should not depend on what happens, you know, inside black hole, what kind of dynamics I have there. Yeah, and even once I choose the surface, what kind of how do I specify the vacuum? Because there are these different states, as I said, there is Hartle-Hawking vacuum, which corresponds to thermal state, and there is Unruh vacuum, which corresponds to evaporating black hole. How do I distinguish between them? What really distinguishes, and what should I do? And to start answering these questions, let's consider a simplified case when we neglect the back reaction of this process of the tunneling field on the metric. And that is okay as long as yeah. Sorry, actually, yeah. Another thing I will neglect is the change in the black hole metric due to evaporation. Yeah, and that's okay as long as the size of the critical bubble that we will be finding, or the bound solution that we will be finding, is less than the evaporation time of the black hole. So working under this assumption, we can treat the black hole metric as static or stationary, properly speaking. Okay, so then we have to go back to the basics and describe the like tunneling amplitude between true vacuum, between false vacuum and true vacuum, as the sum over trajectories or path integral over all possible trajectories in field space. So here I schematically, this dimension is just the field space. So I sum over all trajectories that connect some state close to the true vacuum to some state, some state close to the false vacuum. Actually, yeah, I think it's wrong. So here it's actually false vacuum in the beginning, and true vacuum at the end. Yeah, so some initial state close to the false vacuum to some final state close to the true vacuum. And yeah, I don't write this path integral, but okay, some like path integral over all possible field configurations between these two states. Then when I want full tunneling probability or full decay probability, I also sum over final states in the domain of attraction of the true vacuum. And eventually I get this type of expression, which I don't want you to spend too much time on it. But what is important that I end up with, so basically here I sum over all configurations, which are now defined on a doubled contour that connects the initial time to the final time and then backward to the initial time. Because I mean, where do I get this double contour? Because of this product of the two amplitudes. Yes, so I have like forward amplitude and backward amplitude as well in the probability. And yeah, you may recognize in this expression or in this contour actually the in formalism, which is used in non-equilibrium quantum systems, in particular in inflation, if we want to compute inflationary correlators. Inflationary correlators. Okay, another thing which you recognize in this expression, that here I have this if I rearrange, say, these two terms, I will get inside the projector I. So the projector on the initial state, which is nothing but the density matrix in this initial state. And here I actually know how to generalize the whole formalism to the case when the initial state is not pure. I just have to put inside the matrix element of the initial density matrix, and kind of in this, of course I'm omitting a lot of intermediate steps, but I arrive to the following prescription, that I have to find So now I have this path integral, and I want to evaluate it using saddle point technique, as we do in semiclassical context. My bound solution that I'm looking for is defined on this doubled contour, which lives actually in real time. So it starts from some initial time, which is somewhere on the real axis, goes along this contour, ends up on this real axis as well, and then goes back. With certain like boundary conditions in this initial part of the contour set up by the density matrix of the state I'm interested in, of my initial state that decays. And moreover, what is important, let me emphasize that these boundary conditions, they are actually the same as the boundary conditions for the time-ordered Green's function in the same state. So something like Green's function, I usually know how to compute. So here the prescription is just to take the Green's function, look at it like carefully, and understand what boundary conditions it satisfies at the initial time, and the bound solution I'm looking for must satisfy the same. Good. And also, given that I know how to treat vacuum decay from mixed states, I actually can restrict the whole analysis to outside of the black hole. Because all my vacuum, both Hartle-Hawking and Unruh, they are just some mixed states in this external region. Good, I have 5 minutes. Yes, let me go. Okay, so here I give the summary. Actually, I already summarized it. Yeah, so I need to find the bound solution on this contour with certain boundary conditions. Yeah, here it was some contact with the original Euclidean technique. But yeah, let me skip it. So basically, yeah, we can recover from this more general format. We can recover the standard Euclidean technique for systems at equilibrium. That's a punchline. Yeah, the problem is that finding this bound solution with these boundary conditions is complicated. And in general, it can be done numerically because, yeah, it's just classical solutions. That's important. I mean, we just need to solve classical equations, but that's still complicated numerical problem. So one exercise we did just to demonstrate the feasibility of this technique, but also, in fact, to learn some physics lessons. We considered a toy model in 1+1 dimension, in 2 dimensions, where analytics, where these relevant solutions and tunneling rates could be found analytically. And I think I won't describe what this is. Yeah, let me skip to the results. Yeah, for the sake of time. So what we found in the first attempt, we found the following. We found that the suppression exponent it behaves in the following way. So here I actually have 3 curves, and these 3 curves, they correspond to three physical situations. So the green curve is just thermal rate in empty space. So here for the green curve, I don't have any black hole, and it decreases with temperature, which I denote lambda here. It's just, I mean, this lambda is just proportional to temperature. Okay, it decreases as expected. The blue curve is the tunneling, is suppression of tunneling in the Hartle-Hawking vacuum, and it also decreases with temperature, goes to 0, and it's always the suppression is always smaller than in empty space. So black hole does catalyze like decay actually even on top of just temperature effect. So it has additional catalyzing effect due to some geometric, due to modification of geometry. But I think the most interesting curve here is the red one, and this is decay from the Unruh state. We see that it is more suppressed than the Hartle-Hawking decay, but it's less suppressed than decay in empty space, and it also goes to 0 at high temperature. So that may be puzzling. So it goes against my original arguments, which are my qualitative argument that I presented below, which would imply that Unruh decay should be suppressed at all temperatures, at all black hole masses. But here there is one important thing which actually was missed in this original toy model, namely the effective potential for the modes, for linear modes in this background. It was just like this, and like this is 2D picture, but in 4D, on top of this potential, we also have a barrier which separates the black hole region, which is here, near horizon region, which is here, from the asymptotic region. This barrier in 4 dimensions is due to the centrifugal force. Yeah, it's centrifugal barrier, and this barrier grows with black hole temperature, and that's what gives rise to the gray body factors. So the question is, can we model it in 2 dimensions? And the answer is yes, we could model it in 2 dimensions by introducing additional interactions in this Lagrangian in the action. And here how the result changes. So now the decay from the Hartle-Hawking vacuum, I mean, the suppression still goes to 0 as before, maybe in a bit more complicated way. But again, importantly, the qualitative change happens with the suppression of under vacuum decay, which goes to a constant now at high temperature. The constant, which in our case was just proportional to some combination of parameters of the model, but in the 4-dimensional case, we expect it to be fixed by the black hole. To be fixed again. Well, also by the parameters of the model. You think? Now, so gray body. So what's the lesson here? I think I'm running out of time. So let me summarize the lessons. First of all, the general method to describe this decay, the black hole catalysis of false vacuum decay works. Okay, so it can be applied to a 2-dimensional model, and this 2-dimensional model allowed us to see explicitly how the rate of decay of different vacua changes, depending on temperature, and also depending which vacuum we choose. So for example, this Hartle-Hawking calculation, like Euclidean calculation, it does not give the decay of the realistic under vacuum. So decay of under vacuum is more suppressed than that of Hartle-Hawking in all cases we studied. Though in some cases, if we don't take into account gray body factors, it actually also goes to 0 at high temperature. I mean, the suppression goes to 0, so the decay becomes unsuppressed. But when gray body factors are accounted for properly, the decay of under vacuum, or the rate of its decay, is always exponentially suppressed. So in a sense, these primordial black holes are safe so far. But actually, we still don't know whether they are completely safe or not, because, as I said, we need to actually calculate this rate in the realistic case of 4 dimensions and compare it to the expected abundance of peHs in different models. This approach that I described here, it's actually more general. It applies to other situations out of equilibrium. For example, when black hole is colder than the ambient plasma, we can also use that and see how the temperature of the ambient plasma and the presence of black hole can together catalyze or not catalyze false vacuum decay, and so on and so forth. And in principle, it's even applicable to non-thermal situations, completely non-thermal, when neither plasma nor black hole are in thermal equilibrium with anything. And it's also applicable beyond black holes. Yeah, if somebody is interested in description of tunneling in non-equilibrium systems, that's, I think, is the way to go. Well, and finally, it would be interesting to include the back reaction of the metric and see how gravity affects all these processes. Thank you for your attention. I think I should stop here.
Yes. We'll start with the room, but people on Zoom, please either raise your hand or write something in Slack. From the room, maybe. Okay. Yeah.
I want just to know why it teaches us something about semiclassical quantum gravity. I mean, what was the reason when you mentioned the Hawking was instanton, why it teaches us something about quantum gravity? Could you comment it, please?
Yes. Well, it teaches us about. Okay, so it teaches us about soft quantum gravity, right? So for example, yeah, this Hawking-Moss instanton and Coleman-Delucci instanton, where we can include the effects of gravity, we can see how, like, quantum gravity or gravity affects quantum processes. Yeah, so gravity actively participates in this tunneling process, and yeah, we know, for example, that yeah, the decays. Sometimes gravity actually can shut decays, as we know, of false vacuum. Yeah, like in flat space, when I have a vacuum with lower energy, I would be always able to decay into that. But with gravity, there are examples where the decay is not possible. The Coleman-Delucci instanton doesn't exist. Yeah, and I think this, yeah, does it teach us something that the gravity can change the non-perturbative behavior of quantum field theory? I think it does. So another example I had in mind is that like this Hawking-Moss instanton is known to be quite closely related to stochastic picture of inflation, or the picture of stochastic inflation. Yeah, where yeah, soft modes basically build up and I would say and determine where the universe goes on superhorizon scales. And in that case, again, we can take into account the effect of gravity and build the picture of stochastic inflation together with back reaction on gravity. So yeah, but by quantum gravity I mean soft quantum gravity. Yeah, I'm not thinking about, at least in this respect, in the UV properties of gravity. No. Yeah, I don't know if I answered your question.
There was a question from Lam on Zoom.
Can we manage that?
Lamwe
Lamwe is on Zoom. Can we unmute him?
Yeah, thank you.
Okay.
Thank you, Sergey, for the nice talk. It's good to see you. I have a question about one of your not so technical questions, which is as you correctly pointed out, with gravity. Here, you do not want to do Euclidean time because there are different notions of time anyway. Usually, we go to Euclidean time in order to find the correct path, the bounds. If you keep the time signature without going to Euclidean, do you have to complexify the fields to find the path? Is that what you do?
Okay, very good. Yeah, that was part of, let me go to this. Yeah, that was one of the part I glossed over. So here, yeah, so I start from the path in real time, yeah, which starts in real and kind of goes along real axis, goes back. But you're right that if I just try to find saddle point solution on this path, I won't always be able to do that. Yeah, in some examples I can, and yeah, in the examples we explicitly considered, actually we can, but in general no. And you have to deform this path into complex time. Yeah, basically, like, deformation is allowed because the original path integral does not care what this path is. Yeah, I can deform it arbitrarily. But then for some paths, there is no saddle point of the path integral. For some there is. And yeah, the procedure is to look for such a path. It's a bit of an art, but yeah, this art of finding a right path on which there is a tunneling solution. It should go around, yeah, more technically, it should go around the singularities of the classical solution properly, around branch cuts of the classical solution.
I see. So you are not actually complexifying the fields. You are finding a complex path basically through time.
Oh, both fields are also complexified.
You're doing both. I see. Okay. Okay.
Yeah. Thank you for the question.
Thank you.
We have a question. There's a question from Alex in the back.
Alex Wickman.
Thanks for a very nice talk, and great to see you even in this very, very small window. I have a question. So basically what you showed that the Uru vacuum provides you a finite value of bounds even at infinity. So basically, it implies that still the vacuum catalysis is suppressed. So basically, it does not mean that we should exclude the presence of such a black holes in our horizon, or it does.
Depends on the value. Yeah, depends on this value, asymptotic value. Okay, in our toy model, it's controlled by a parameter q, which can be, well, actually by this parameter q times L, which can be from 1 to 0. I mean, from 0 to 1. Yes, so in principle, I mean, we can play with this. This is toy model. Yes, so now the real challenge is to take, say, Higgs potential and find what this asymptotic value is for the actual Higgs potential in 4 dimensions, and then it will depend. Yeah, if it's a few hundreds, perhaps we are safe. If it's a few tens, then we should compare it to the expected abundance of these primordial black holes in given models. You see, because the statement of this catalysis. Yeah, so imagine. Okay, for a single black hole, indeed, say this process is still exponentially suppressed, but you have many of them. You have a humongous number of them in the universe, and one of them may well trigger this decay. Yeah, so it becomes a quantitative question.
But what do you expect? Is it larger than what is it for realistic Higgs, so to say? Is it tens or hundreds? What is your
expectation? No, for Higgs we don't know. We don't know yet. No, we are not yet there. But for example, the number of black holes that people, like in some models where people discuss the production of these primordial black holes in the early universe, in our universe, it can be 10 to 40. Okay, so 10 to 40 black holes. So now I need to compare the decay probability for Higgs. Is it bigger or smaller than 10 to minus 40?
Okay, thanks.
Sergey here.